Hi, everyone. We are going to continue into chapter 8. We are almost through with all of Orgo 1. We'll be wrapping up in chapter 9. Chapter 8 is going to be a continuation of reactions that we see with alkenes. So remember, we talked about chapter 7. An alkene is a hydrocarbon with a double bond. We talked about naming alkenes, and in particular, we talked about the E and Z nomenclature for alkenes. So make sure that you understand this nomenclature before progressing on. In the last chapter, we also talked about how to make double bonds via an elimination reaction. So this is a type of reaction that condenses two bonds by removing, for example, hydrogen and OH, removing water to condense into a double bond. And today what we're going to be talking about is actually the reverse, which is opening up double bonds in what's called an addition reaction. So today is going to be talking about addition reactions. First, let's dive into some of the properties of the double bonds. This is a continuation of properties of double bonds. In particular, properties when looking at the double bond compared to the single bond. So one of these addition reactions that we'll get into more is called a hydrogenation. This is where you add hydrogen across a double bond. So we're taking a double bond and adding hydrogen. You can see each hydrogen is then added onto the molecule and it breaks the double bond. And that forms or just leaves behind a single bond. So you go from a molecule that has a double bond and you're just turning it into a single bond. One of the main things you can see here is that to go back and forth, right, to make a double bond, you need to remove two hydrogens, or vice versa. To take a double bond and make it a single bond, to break it, you need to add two hydrogens. This is a main principle in talking about something called the saturation of a molecule. So when something is fully saturated, that means that it has only single bonds and it has all of the hydrogens possible attached to carbons. Now, this word gets used a lot. You've probably seen it with fats, and that's because fats are hydrocarbons. So we've talked about things where you've probably seen names like saturated fats versus unsaturated fats. And the only difference between these two is that saturated fats have only single bonds. They don't have any double bonds, and unsaturated fats have double bonds. So we know how to go between double bonds and single bonds via this hydrogenation reaction. And actually, this is used commercially to take unsaturated fats and make them saturated fats. So if you've ever seen things like margarine, which is oil that's been made into a solid, so it's like butter, they do this process. They take double bonds and they make them into single bonds via hydrogenation. They make them into saturated fats to make it more solid. This process is generally exothermic, which means, again, it releases heat. The process of making single bonds releases heat, and that's because you're breaking that double bond, you release a lot of heat and create energy. The other key thing for a hydrogenation is that it requires hydrogen, or it requires a catalyst to activate the hydrogen. So you have to have a metal catalyst, which a metal in general that helps the reaction along. And typically it's one of these metals. So platinum, palladium, nickel, or rhodium are the common catalysts that are used for this reaction. The metal catalyst is what's doing the job of splitting the hydrogen so that they actually are sticking up on the metal surface. So you can see these teal colored spheres are the metal. This could be, like I said, platinum or palladium. And platinum, palladium, all of these metals, the reason they're good catalysts is because they bind single hydrogen atoms like this. So now they have just a hydrogen atom sticking off of the metal. And when the double bond approaches the metal, it can pick up one of these hydrogens. Now, because this reaction happens in a way so that all of the hydrogens are on one surface sticking up, they can only ever add to one side of the molecule. So we call this syn addition. This is important more so for when you see a ring, for example, and we'll talk about this more, but hydrogens in a hydrogenation always add on the same side of the molecule. You can see they've pushed up the rest of whatever is bound to this particular double bond. There's now a single bond there, and we've added our hydrogens on the same side of the molecule. Okay, so thinking about the idea of hydrogenation, the very simplistic breaking a double bond, making a single bond by adding hydrogen. Let's try a question where we're using all of the things we've learned, so going from name to drawing and looking at a reaction. So if you start with 2-methylbutane and you do this catalytic hydrogenation, what product would you make? So first, I suggest we draw out the starting reactant, 2-methylbutane. So you need to know how to go from the name to the drawing. Butane is a 4-member alkane. So 1, 2, 3, 4. And it has a methyl group on the 2 position. So I'm going to number starting here, 1, 2, here's our methyl group. Sorry, my pen is a little jagged today. I actually had to get a different pen for this today, and it's not as good. Okay, so this is what we want to produce. This is the single bonded alkane we want to make. Which of these double bonds would produce that? So let's think about if we broke open these double bonds with hydrogens, what they would look like. So for example, on number 1, you would get rid of this double bond. So imagine that gone. You add hydrogens on, so it would just be single bonded now. And if you were to name this or look at the structure that I drew, you'll see that this does match. So 1 is a match. If I removed that double bond and if it was just single bonded, it would be the product I was interested in. Okay, what about number 2? If I get rid of this double bond, you can see that number 2 actually doesn't match. And in fact, the name of this product, if you wanted to try to name it, this is a butane still, but it is a 2,3-dimethyl butane. So number 2 is not going to work. What about number 3? What if I erase this double bond? It doesn't match my drawing per se, but if I was to name this, remember that I'm always going to name my substituents with the lowest number. You'll actually see that this is the same as number 1. This is a butane. It has one methyl group on it, and the methyl group is in the 2 position. So this is also 2-methylbutane, and you can see if you flip this around, it will be the same as the drawing number 1. What about number 4? If I removed this double bond, just made it a single bond, if you count here, the longest chain is 1, 2, 3, 4, 5. This is a pentane, so this molecule will not equal our product. So in this case, our answer is 1 and 3. Now, as I said before about the syn addition, hydrogenation always adds hydrogens on the same side of a molecule. So when you have a ring, this is particularly important because that means that the hydrogens add in a cis product. They will not make a trans product. They'll always add on the same side of the molecule. So for example, if you start with this dimethyl cyclohexane, 1,2-dicarboxylate, so the carboxylates are attached to a double bond. Currently, there is no cis or trans here in particular. But when we add the hydrogens on and remove the double bond, you'll see that the hydrogens will add onto the same side of the ring, so both in the down position, leaving the other 2 groups in the up position. Now, both hydrogens could have added on the up position, leaving these in the down position. That wouldn't have mattered. The point is that they always add to the same side, making them a cis product. They will not add opposite of each other in the trans product. So we've talked a little bit about the stability of branch chain alkanes and also alkenes, and what is noted is based on the heat of hydrogenation, we can get some more information into how stable double bonds are. You'll notice that the heat of hydrogenation is higher when you have this less substituted bond, this change in energy here. So more stable alkenes have lower heats of hydrogenation. And as we become more substituted, you get more stable and lower heat of hydrogenation. And also looking between a cis versus a trans double bond is more stable and thus has a lower heat of hydrogenation. So the key takeaway here is that we remember that double bonds that are more substituted equals more stable, and things that are trans versus cis are more stable. And the more stable, the lower the heat of hydrogenation. This is the same stability trends we saw with heats of combustion. And again, exactly as I said, substitution stabilizes alkenes. And if you are trans or the E form of a double bond, it's more stable than the cis or Z form of the double bond. Another property of double bonds is that they are nucleophilic. The electrons in the pi orbitals on that double bond actually form a region of electron density. And so in this region of a double bond, they're very nucleophilic, meaning they can act as a Lewis base. And that is the key principle for our reactions we'll be talking about today, the addition reactions. Double bonds themselves act as a Lewis base, meaning they like to give electrons. Remember, Lewis bases donate electrons. And so they are nucleophilic. Nucleophiles are Lewis bases which donate electrons. So if you treat a double bond, which is a nucleophile, with something that is electrophilic, an electrophile, which means something like a Bronsted acid or just a Lewis acid, any acid in general, you'll have a chemical reaction. And this particular reaction is called an electrophilic addition. And that is the addition reactions we'll be talking about today. So here's an example of a Lewis acid with its region of positive. This is a hydrogen here. A nice slightly positive hydrogen will react with this slightly negative double bond. So let's go into addition reactions. The general idea of addition reaction is the formation of two new bonds on a double bond in which you have some A and some B within your molecule that add across this double bond, the pi system. Generally, often this A and B are very polarized. So it's a polar bond that is holding A and B together. The addition reaction is very valuable to synthetic chemists. And the reason that these get done often is because these products are very good for the formation of other further reactions. Double bonds and alkenes are also very readily available, so they're an easy reactant to start with. Some of the addition reactions that we'll be looking at are shown here. We've actually already talked about a hydrogenation reaction where you add hydrogen across a double bond. You can add, for example, a halogen acid. So here is HBr. You can add it across a double bond, or just a halogen gas, so just bromine gas, Br2, across a double bond. These are all variations of the addition reaction, and there are many more variations of it. And we'll see these examples, but essentially they follow the same general pattern, which is that you break this double bond and you form two new single bonds on the carbons. They're essentially the opposite of an elimination reaction, where we took two things and we removed them, and through that removal we closed up and formed a double bond. A lot of these reactions have a strong preference for forming one regioisomer over the other, and this is called regioselectivity. We've talked about regioselectivity in our substitution reactions, actually. So when you have an alkene and there are two different sets of substitutions that could happen. For example, when you have something with an A and a B, two different things that we'll be adding across. Here we're using H and Br. Technically, there are two different products that could form from this, right? We could add the hydrogen on the 1 position here and the Br on the 2 position here, that would result in this product. Or we could do it the other way around. We could add the Br on the 1 position and the hydrogen on the 2 position, and that would give us this product. Now there is actually a variation, there is a selectivity that these tend to bind in. And this follows what's called Markovnikov's rule, which is that the hydrogen in this case ends up bound to the carbon with more hydrogens on the alkene. So here's another example of a double bond. And if we were to draw out all the hydrogens that are not visible, you'd remember that there's a hydrogen here and there's not a hydrogen there. There's a hydrogen on number 2 and there's no hydrogens on number 1. So the hydrogen will bind where there are more hydrogens, which is here. And the bromine will then thus bind to the other spot. The other way to think about this is that the X, the non-hydrogen component, in this case bromine, ends up on the more substituted carbon, the carbon that is more substituted. So this carbon on the double bond is more substituted than this carbon. And so the bromine will go to the more substituted carbon. And thus will result in this product, not the product where bromine goes on the less substituted carbon. Here's another example down here. This is using HCl. And again, you can think of it that the chlorine will go onto the more substituted carbon and the hydrogen will go onto the least substituted carbon, making this the major product. Hydrogens go where there are more hydrogens, where it is the least substituted, and the carbon attaches to the more substituted. So now we're going to delve into each of these reactions. I've shown you the general idea of the reaction and how it generally the mechanism for how the addition occurs, but let's break these down. So first, we're going to explore this HX type of addition. So when you have addition using HCl, HBr, or any other acids in general to an alkene. All of these additions, when you have an HX addition or with any other acids, follow what we just went over, which is Markovnikov's rule. And the mechanism of the reaction is thus. First, the alkene is protonated. So here the double bond, which is a nucleophile, is going to use its electron density to grab a positive hydrogen. So it's donating its electrons to the hydrogen, and it will bind that hydrogen. That is the first step. When this happens, we form a carbocation. So this is key in these HX reactions. You form a carbocation for this type of addition. And notice that when our hydrogen binds on the least substituted carbon, that means our carbocation is on the most substituted carbon, and this is good. Remember from our substitution reactions that you want the carbocation on the most substituted position. So the next step then is to grab that leftover chlorine, or in X in general, the conjugate base, which will then add onto the carbocation, forming your product. So this is the reason you see the X or the general conjugate base added onto the more substituted position. It has to do with carbocation stabilization. So again, to reiterate, here's another example. This is we're adding HBr to this double bond. Now what's not drawn here is that there are two hydrogens. Don't forget, there's a hydrogen and a hydrogen here. So here, first step is going to be to protonate. And we want to protonate in a way that it's going to break our double bond and form a carbocation. And the carbocation wants to be on the most stable position. So notice that we would not protonate here. That would make a primary carbocation. Instead, if we put our hydrogen here, this leaves us with a tertiary carbocation on the other side. So the hydrogen will add in a way that leaves the more substituted carbocation because this is more stable. And so once that carbocation is formed, our conjugate base can add in forming the product. Okay, so let's think about carbocation formation via this question. Which carbocation forms when 3-methyl-2-pentene is protonated? So first, let's draw this molecule, 3-methyl-2-pentene. So it's a pentene that is 5-membered, 1, 2, 3, 4, 5. The double bond is in the 2 position. It is 2-pentene. So let's number these. It would be here. And our methyl is in the 3 position, which is here. Okay, so if I were to protonate this is going to take away my double bond and add a hydrogen. Would my hydrogen add on this end or this end? Remember that if I add a hydrogen on one end, the carbocation is going to form on the other side. So either I form a carbocation here or here. In this case, the more stable carbocation would be in this position here, because this is a tertiary carbocation versus here, which is a secondary carbocation. So B would be the answer. In general, these additions of HX follow the stability rules we just talked about, which is that hydrogen adds on to the carbon of the alkene and halogen on the other to generally form this alkyl halide where the X is on the more substituted carbon. Generally, for this type of reaction, a more substituted alkene reacts more rapidly. As just a general, the more substituted that alkene, the faster this type of reaction will be. And that's because we will have the ability to stabilize that carbocation better during the transition state. Also, picking the actual acid you use for this reaction can make it faster. So a strong acid like HI is going to react faster than a weak acid like HF. Now, because this reaction goes through a carbocation, when we talk about the stereospecificity of the HX type reaction, you'll note that the face of the attack doesn't necessarily matter. This is true for any type of carbocation intermediate reaction. This is true for reactions as in our SN1 reactions where we form a carbocation as well. You have a mixture of products, and that's true also for this type of addition reaction. So once you, for example, protonate on this ring, the opposite carbon then forms a carbocation, and our chlorine can attack from either end. This carbocation is free for attack on either side. There's nothing necessarily blocking it. And so you can have a syn or anti-attack. So that means you'll have a mixture of products as far as the specificity of the stereocenter. Now, the products might not necessarily be equal 50-50 because of groups. If there are bulky groups around, it might make it less likely for one side to be attacked versus the other. But generally, both sides are open for attack. You can also have rearrangement in these types of additions. Remember, this is also true for any type of reaction where you have this carbocation formation, just like in our substitution reactions, same idea, same concept. When you form that carbocation in the protonation step, for example, you can have rearrangement after the formation of the carbocation to help stabilize that carbocation. So for example, here, when we react methyl 1-butene with HCl, we protonate. And in this case, here's our double bond. The protonation would happen in a way that our carbocation would form on the more substituted carbon, which would be here. However, we can have a hydride shift. This is one away from our carbocation position. And when we shift that hydrogen, it makes a tertiary carbocation, which is more stable. So again, you want to look out for the potential of a secondary next to a tertiary position in these reactions, because those are when you are likely to have some type of hydride shift or methyl shift to form this more stable cation. Okay, let's try another example. What is the product of the reaction of 1-methyl cyclohexene with HCl? So this is an HX reaction. We're going to add hydrogen and then chlorine. And our starting reactant is 1-methyl cyclohexene. So let's draw that. It's a cyclohexene. Cyclo-hex is 6-membered ring. Here's our double bond, and our methyl group is on the 1 position. Remember, I can always number any way on these rings. I'm going to put it here. We'll call this our methyl group. Okay, so here is our ring based on the name. When adding our hydrogen first, we're going to get rid of our double bond and form a carbocation on the opposite position, on the position that is more substituted. So our carbocation should form here, and the hydrogen will add here. That means after this carbocation is formed, our chlorine will add where the carbocation was, which is in the more substituted position. So ultimately, we should have a ring that looks like this, which would be A. Okay, so let's move on to our second named type of reaction. This is another type of addition reaction called the acid catalyzed hydration. Acid catalyzed hydrations are very similar to the HX additions. This is where we're using a strong acid with water to form H3O+. And ultimately, this is going to form a very polarized bond in water, very similar to the HX bond. Here, we're instead adding a hydrogen and an OH across a double bond to form an alcohol. So we start with a double bond, an alkene, and end with an alcohol. Again, this is very similar to the addition type we just talked about, the HX addition. It follows the same rules. The reactivity and selectivity are the same. So it is going to form the OH on the more substituted carbon when you open up that double bond. So you can see here, if I opened up 2-methyl-2-butene, the OH group would go on to the more substituted, and the hydrogen would go here, making this product. So more substituted alkenes generally react more rapidly for a acid catalyzed hydration reaction. The mechanism of this is, again, very similar to the HX mechanism. Here we do a protonation first. This is a protonation from the hydronium ion. This is formed from our acid. So again, when you add acid and water together, you make this hydronium ion. That's why the acid is needed for this type of reaction. So this hydronium ion is going to protonate the double bond. Double bond opens up, it's a nucleophile, it grabs this hydrogen and forms a carbocation. That carbocation is going to form on the more substituted carbon to be stable. And this is the slow step of the reaction, just like in our HX reaction. Once you form that carbocation, then we can add the water onto the carbocation. Now notice this doesn't add initially as an OH. It's going to add as water, and that's going to happen very quickly. So next you'll have this ion in which water is bound to your carbocation. The third step, this is the one step that is different from our HX reaction. We actually will then deprotonate the water to form an alcohol. And this happens via another water molecule that it's around. And look, we make our hydronium ion again so that this can continue to react with other double bonds, forming our alcohols. This is also a very fast step. So ultimately, we end with an OH that is an alcohol bound to the more substituted carbon where our double bond was. Okay, let's think about an example of this type of reaction, knowing what we know of our HX and our hydration reactions. If we did a acid catalyzed hydration of Z3-methyl-2-pentene, what would the product be? Well, first let's draw this. So we know we have a pentene. That's 5, 1, 2, 3, 4, 5. The double bond is in the 2 position. That would be here. There's a methyl on the 3 position, which is here. And it is a Z-shaped double bond. So remember that Z means Z same side, right? So that means the large groups are on the same side. Currently, if we look at our double bond, these are the groups it has on it. Here's a methyl group here, a hydrogen here, this chain, and this methyl group. So currently this is actually in the E formation. It is in the trans or E formation. And if I wanted to redraw this so that the big groups are on the same side, remember all I have to do is switch one of these around. I'm going to switch this one here. So that it is pointing up and my hydrogen is here. Okay, still the same thing. 1, 2, 3, 4, 5. It's a pentene. The double bond is in the 2 position. The methyl is in the 3 position. I just now have my groups pointed in the direction so that it is a Z double bond. Okay, so let's do acid catalyzed hydration. So remember on this, we're adding water, and you can think about it adding a H and an OH. The H will add on the least substituted carbon and break the double bond. So that would be here and form a carbocation here. And our OH will bond on the most substituted carbon, which is where we have our carbocation, which is there. Okay, so now our final product, if we were to draw this out, it's a 1, 2, 3, 4, 5 membered alkane. There's no Z or E here because there's no double bonds. Our methyl group is on the 3 position, and our OH group is also on the 3 position. So this should be a pentanol, that is OH on the 3, so 3 pentanol, and methyl on the 3, 3 methyl. That makes D the correct answer, 3 methyl, 3 pentanol. Now, these types of hydration reactions are actually reversible, and I actually talked about them in our elimination reactions. I talked about a dehydration reaction, which is the elimination of an alcohol and a proton to form a double bond. It's the exact opposite of this reaction. So these actually are reversible. You can go between the elimination and the addition. The whole reaction is a reversible reaction. So here, for example, an alkene in water with an acid will result in an alcohol, which could also, using that same acid, reverse back into forming the double bond. The way to adjust this reaction is by using Le Chatelier's principle, which is just by imbalancing the reaction to drive it in one direction. So for example, if you add water, you add to the reactant side here, it will cause the reaction to advance to the right. It'll make it form more alcohol. So an excess of water is used for the hydration reaction. And if you remove water, you have a low amount of water, it will drive the reaction to the other direction, driving it to the dehydration side to form our alkene product. Okay, let's talk about one more variation, which is the addition of halogens. Halogens as a gas, which is X2, any halogen in general, can also be envisioned as an electrophile, and that's because a halogen is a good leaving group. So remember, our double bond is a nucleophile, and we can have electrophilic halogenation of these two X atoms across the double bond, across the alkene. These add in a way that obviously each side is going to add evenly. You have the same thing, a Br and a Br, or a Cl and a Cl. So we don't have to worry about Makovnikov's rule, in which we are looking at where the proton will end up, or where the OH will end up on more substituted or less substituted, because we have two of the same thing. Now, there is something particular about these types of reactions. They are stereospecific. We talked about how on a reaction with an HX or with water, they are not stereospecific, and that's because of the carbocation that's formed. So when we make our products, because your addition of a chlorine or OH can go onto either side of the carbocation, that makes them non-stereospecific. These additions of halogens in a halogenation are stereospecific, and they always form in the anti position. They always form anti of each other, so one chlorine will add up, the other chlorine will add down, for example, across a double bond. And the reason for this is because during the mechanism of a halogenation, you form a halonium ion. This is an ion in which you have the carbons that were previously in your double bond forming this three-membered ring with your first halogen to add. So the first halogen adds onto the double bond, breaking the double bond. And instead of forming a carbocation, so instead of forming a ion on the carbon, it instead forms this halonium ion. And then your second halogen adds. And because this three-membered ring is formed on one side of the double bond, it means that the other ion only has the potential of adding on the opposite side, because our now halonium ion is blocking one side. So the formation of the halonium ion in this type of reaction is the rate determining step. Similar to our other types of reactions, more substituted alkenes are going to react more rapidly. That's the same. It's just that we always are going to form this anti-formation, because a halonium ion is actually more stable than forming a carbocation. So in the case of a bromine addition to cyclopentene, what would be our particular product? If cyclopentene looks like this, a five-membered ring with a double bond, we would add our bromines on to this double bond one at a time. And because of that halonium ion, you would add bromines anti to each other. So there is stereospecificity. These would be opposite of each other, one up, one down. So our answer should be A. You can also have a co-halogenation reaction in which you're adding water and a halogen together. And in this case, you add a bromine followed by a OH group. So the halonium ion is going to form, and then the OH will form. So no carbocation here. You do form a halonium ion, but instead of the second bromine being added on, you form an OH added on, followed by an OH. These also have the same stereospecificity that we saw with a regular halogenation, and that's because the halonium ion is going to form blocking one side, so you have anti-formation. So here we can add, for example, an OH and a chlorine or an OH and a bromine in a way that is anti to each other. Notice also that the second product, in this case the OH, is always going to be on the more substituted side of the double bond if that is the case. So they add anti to each other and the OH is on the more substituted end. And I just want to bring up again, we talked about this at the very beginning of the talk, but when we do a hydrogenation, which is two hydrogens adding, remember that this does not happen anti to each other, it does not go through that halonium ion, and instead hydrogens add syn to each other, so on the same side, and that's because of this platinum or other metal catalyst. Review that from the beginning of the lecture. But just as a reminder, hydrogenation acts on the same side. This halogenation adds anti to each other. Okay, well, that's it for this chapter. We're going to continue on with some reactions, addition reactions and other reactions of the double bond in the rest of chapter 8.